A developer feeds a massive prompt into a large language model. The GPU starts processing, but suddenly the entire system grinds to a complete halt. The culprit behind the crash is the key value cache, or KV cache. You can think of this as a high-speed digital cheat sheet. It stores previously processed tokens so the computer can retrieve them instantly, allowing the model to avoid doing the exact same math twice. The problem is scaling. As the context window of a prompt gets longer, the KV cache expands exponentially. It consumes vast amounts of space until the GPU literally runs out of physical memory. The AI industry wants to build models capable of reading entire books or codebases in seconds. That ambition is currently blocked by the hard physical limits of our hardware, making the KV cache the ultimate bottleneck. To shrink these massive, high-dimensional data arrays, engineers rely on a classical data compression technique called vector quantization. But traditional quantization methods carry a massive penalty. Techniques like product quantization require the system to calculate and store custom constants for every small block of data. This creates a permanent memory overhead, like a heavy dictionary permanently attached to the data, which often defeats the point of the compression. The second flaw is mathematical. Traditional quantization alters the inner product, the operation AI uses to judge similarity between two concepts. Compressing the data slightly shifts the vector's trajectory. It breaks the mathematical alignment the vector once shared with related concepts. When that inner product is broken, the AI loses its ability to accurately measure relationships. It fails to retrieve obvious data and begins to hallucinate. To scale AI effectively, developers need a compression algorithm that requires zero memory overhead and preserves the exact inner product math that gives the model its intelligence. Researchers at Google have introduced a solution called TurboQuant. It functions as a two-stage assembly line, precisely compressing massive vectors down to just 3 bits per number. Step 1 is polar quant. Instead of Cartesian coordinates navigating 3 blocks east, 4 north, it converts vectors to polar coordinates, mapping a total distance at a specific angle. TurboQuant then randomly rotates vectors, simplifying geometry and snapping data into predictable, evenly spaced patterns. Because the pattern of these angles is now known and highly concentrated, the data maps perfectly onto a fixed circular grid. The model no longer needs to calculate or store custom boundary lookup tables. This initial polar mapping uses the vast majority of the available bits. It captures the main strength, direction, and concept of the original vector. By changing the geometric perspective from square grids to circular coordinates, TurboQuant entirely removes the memory overhead penalty that crippled older methods. PolarQuant drastically reduces the overall file size, but it leaves behind a tiny spatial gap between the original vector and the compressed version. There is still a microscopic mathematical bias in the inner product. If left alone, this leftover bias means a vector similarity search would return slightly inaccurate attention scores. Step 2 is the quantized Johnson-Lindenstrass transform, or QJL. Acting as a mathematical fine-tuner, QJL targets the residual error. It crunches leftover bias down into a single sign bit, plus or minus 1, mathematically pulling the vector back onto its true path. Combining the broad strokes of polar quantization with the 1-bit QJL fix produces a hyper-compressed vector that is perfectly unbiased. This two-step architecture resolves the traditional tension between compression and precision. It achieves high reduction model sizes without corrupting the AI's internal logic. The practical proof of this architecture comes from the needle in a haystack test, which measures if a model can find one specific tiny piece of information buried inside a massive amount of text. This chart plots retrieval accuracy against context length. As the context grows, standard compression methods drop off in accuracy. The 3-bit TurboQuant method maintains a perfectly flat line at 100%, acting identically to the uncompressed baseline model. TurboQuant achieves perfect retrieval while taking up 6 times less memory space than the full precision baseline. Shrinking the data footprint produces a secondary benefit: processing speed. Moving less data through the hardware means the system operates at a much higher frequency. In testing, 4-bit TurboQuant delivered up to an 8x performance increase on H100 GPUs compared to unquantized keys. Vector indexing time dropped to virtually 0. By shrinking the data footprint, TurboQuant accelerates the entire computational pipeline, turning a known system bottleneck into a performance multiplier. This diagram illustrates Shannon's lower bound, the absolute mathematical floor for data compression allowed by physics. You cannot compress data past this line without destroying information. Proofs confirm TurboQuant operates verifiably near this limit, settling just a fraction above the barrier. For developers building large language models, this means the KV cache memory problem has a mathematically sound solution. For the broader industry, it provides the mechanics to build billion-scale semantic vector databases that operate with the efficiency of a 3-bit system, while maintaining the precision of models exponentially larger. By pushing vector compression to its absolute mathematical limits, billion-scale semantic databases and long-context LLMs can now run with state-of-the-art accuracy on standard hardware.